Okay, everyone, and thank you for coming to the first climate snack of the season for new and the fifth climate snack in total. For new attendees, climate snacks are digestible talks on climate-related topics, and we hope to bring a wide range of backgrounds from the audience, in terms people from academia, but hopefully also outside academia and people working on different disciplines. And we usually bring experts in two main categories. First, people with several decades leading the field, people already consolidated, and second, also rising rock stars that are pushing the limits of the field right now. Today, we have Susan Cook-Patton, who clearly belongs to the second category. Susan is a forest restoration scientist on the Natural Climate Solutions Science team at the Nature Conservancy. And she has over a decade of experience leading scientific investigations into how changes in biodiversity and climate are impacting forest ecosystems. As you know, the topic of forest carbon sequestration in forests has attracted a lot of attention in recent years, and also it's been object of some controversy with lots of different estimates in the literature. In my opinion, Susan has published the most comprehensive synthesis of carbon accumulation rates in forests, and today she will share her insights as a leader in the field. So, Susan, please.
Great, and you can hear me okay? So thank you so much for the invitation to speak at your first climate snack. I love the name. I do have a confession before I start, which is that my kid woke me up at 2 a.m. and I never managed to go back to sleep, but I think I'll be fine. But if you will do me the favor and assume that if I'm not making sense, it's me, not you, and please just ask clarifying questions. And this will be fun to see what I come out of my mouth. All right, so I work on climate change. I have to start the presentation with sort of, the downer side of climate change. There's no way around it, which is that climate change is here and now. This was the study that came out last year that estimated that climate change impacts have already been documented across 80% of the globe, where 85% of the population resides. And unfortunately, we don't even need this study anymore to make that point. I give a lot of talks and usually start with like, here's an example of a climate impact. And I used to have to dig around for these, but now, I just go to my local newspaper and there is a news story practically every day. This was the one that was there when I put together this presentation, which was that there's extreme rainfall events in Wisconsin smashing the daily record with 9 inches of rain, causing all kinds of flooding. But I'm not going to leave you with the downside of climate change. I feel incredibly lucky that I have a job where I get to focus on finding solutions to what is the biggest challenge that our world has potentially ever faced. And that's what gets me out of bed in the morning and keeps me from pulling the covers over my head and just giving up. But this was the first.
And your kid too, right?
Yeah. Well, that was, I thought long and hard about whether to have kids. I have 2 of them. And yes, I thought, okay, I'm going to have kids, but I'm going to fight every day to try to leave them a better future and the rest of the world's children, and frankly, us, because, it's here now. So this was the first paper that came out from my team. I'm not a co-author on this, but it's definitely informed my work, where the goal was to quantify all the different ways that we could use nature to help tackle climate change. And we call these things natural climate solutions, which are actions to either avoid greenhouse gas emissions or capture additional carbon through improved management, protection, restoration of forest, wetlands, grasslands, and agricultural lands. Unlike other sort of more technological solutions like direct air capture, these natural climate solutions can come with a whole host of co-benefits like the promotion of sustainable industries and jobs, clean air, clean water, protection of biodiversity, and supporting and enhancing the resilience and livelihoods of those who most intimately rely upon the land. And this is the main figure that was in that first natural climate solutions paper. There's a lot here, so I'll break it down into what the different components are. So the size of the bar is the maximum mitigation potential with safeguards. Those safeguards mean they put in factors that protect food security and the human needs for food, fiber, fuel. So that's maximum with safeguards. And then this sort of lighter gray is opportunity at $100 per ton, which is much higher than the current price on carbon, but it's what we call the social cost of carbon. And it's the idea that we are going to have to pay, and we are already paying a lot of money to adapt to and clean up from the negative effects of climate change. So better to pay that $100 now to stave off the worst effects of climate change than to pay it later to mop up from the mess. And then we'll have a lower cost opportunity. I have $15 here, but actually in the main figure here, that's actually $10. So a lower cost portion of that opportunity. And then we've got them coded by different co-benefits that they provide and an attempt to provide uncertainty around those estimates. One thing I wanted to add with respect to the social cost of carbon is when they put this paper together in 2017, $100 was our best estimate of what that cost should be. But this was a paper that just came out, I think maybe a week or two ago, where they estimate that actually $185 per ton of CO2 is a more appropriate cost. So that makes sort of land sector opportunities actually look quite cost effective. And we estimate that there's up to 11 tons or petagrams of CO2 per year possible at $100 per ton. Compared to more technological solutions, which we will need as well, those just aren't as cheap at the moment. So direct air capture, which is sort of the closest thing to a tree sucking CO2 out of the air, is costs about $600 per ton of CO2 currently, and with hopes of soon making it $94 to $232, but again, still quite expensive. Okay. This is just another way of looking at that figure. 11 gigatons, petagrams is the contribution that we think nature can provide towards tackling climate change. But another important point here is we definitely need transitions towards clean energy sources. Fossil fuel emissions are the most important climate solution, but that said, reductions in fossil fuel emissions are the most important solution. We're still going to need to draw additional carbon out of the atmosphere, and the land offers some of the most promising opportunities to do that at the moment. And the opportunities are divided across protection actions, which, sorry, I'll start with managed. Managed actions have about 5 gigatons, then protection, and then restoration. So restoration tends to be more expensive. So my first key take home here is that all climate solutions are needed, but especially reductions in fossil fuels, but that nature offers many deployable and scalable climate options. If for the purposes of today's talk, what I want to focus on is this first bar, which here we've called it reforestation. It's the largest single opportunity unconstrained by cost. I'm using the term restoring tree cover, and just to be clear what that means, it means sort of putting trees back in places where they historically supported forests. Sometimes people use the term afforestation for this, but afforestation could also mean putting trees where they'd never belonged, like native grasslands. So we don't want to do that. That's bad for biodiversity. Trees often don't survive, prone to drought conditions and fire, et cetera. People also call it forest restoration, but that there's so many things that count as forest restoration. That's too big of a term. Reforestation is another common term. And I put in agroforestry here too, because I'm looking at lots of different ways for getting trees back into the landscape. So the first paper that I told you about was the global study, but we soon realized global numbers are good for sort of giving you an overall sense of what's possible, but what we really needed were national level estimates of what's possible, because those are the numbers that help to drive policy agendas. And so we did one for the United States, and again, restoring tree cover was the largest opportunity that we found within the US. We did it again for Canada, and for this one, restoring tree cover is actually not the largest opportunity. The bigger opportunities are in the agricultural sector overall rather than forest. And the single biggest opportunity was in protection of grasslands and peatlands. But the thing to remember about trees in Canada are that they're slow growing. And you also have to account in many places for albedo, which is the warming that comes when you put dark trees on snow-covered landscapes. It can cause actually more net warming than the cooling benefit that you get from drawing CO2 out of the atmosphere. So accounting for both the slow growth and albedo leads to low mitigation opportunity in 2030. But if you run the clock out farther, that opportunity grows 16-fold and making restoration of tree cover one of the largest opportunities. It just takes time to achieve the benefits. So that's my next take home, is that restoration of tree cover in particular is a powerful climate solution, especially if deployed sooner rather than later. Now, if you've been paying attention, you maybe noticed I have a little asterisk up here by largest. And that's because, as I've mentioned already, it's quite expensive compared to other natural climate solutions. This was another paper that we did looking at the potential for low-cost restoration of tree cover reforestation across the tropics. It was a top-down econometrics model where basically you look at land cover change, or the signal of going from not forest to forest in the Hansen data set, and combine that with gross agricultural revenue of 21 of the top dominant crops in those lands, plus some known drivers of forest cover change like slope and elevation, distance to cities, et cetera, and said, okay, when you see forest come online in the Hansen data set, how is that associated with changes in agricultural revenue? So the idea is, as agricultural revenue goes down, reforestation goes up, and you can use that switch as a price signal to estimate how much you might need to pay people to get reforestation to happen. And what we found, the green on the top is for restoration of tree cover, and the orange on the bottom is for avoided deforestation. And the main thing to notice here is the scale. So restoration of tree cover goes from 0 up to 35 tons of CO2 possible at a price of $20 per ton of CO2. Whereas at $20, you can get up to 500 plus tons of CO2 from avoiding deforestation. So on average, we found that avoiding deforestation was in the sort of 7 to 9 times more cost effective than restoring tree cover. And of the 90 countries that we looked at, only 21 countries had more mitigation potential from low cost restoration tree cover than avoided deforestation, and 17 of those are in Africa. The other reason we have a star up by largest is that there is a very large error bar around the estimated size of the overall mitigation potential. This is from that original Griscom et al. 2017 paper. And the error bars were so large, they went off the figure. So they just put a little star to indicate that. But the actual range goes from 2.7 petagrams of CO2 per year up to 17.9 petagrams of CO2 per year, which is a 15 petagram range for something that's about 10 petagrams of opportunity, which means the confidence range is 50% greater than the estimate itself. And I often say that this error bar is the reason I got my job, because they recognized they needed somebody to come in and improve our understanding of the mitigation potential of this opportunity. So that is what I've been doing for 6 years now. So I work at an environmental NGO, And I often get emails like this, which says, Susan, if I do this sort of project in this location, how much carbon can I get? Ballpark number by the end of the day is fine. Like, I need it for a proposal. I need it for some strategy development. And frankly, I hate these emails because I'm a scientist, right? And I want to get people good carbon numbers, and like ballpark just doesn't cut it. People don't ask me for ballpark anymore. And the reason it's not possible to just sort of shoot off a quick and easy number is that your mitigation potential is going to depend on location. Are you in a dry tropical forest? Are you in a wet tropical forest? It's going to depend on the approach you use. Are you putting up a fence, taking off the cows, letting the forest regrow naturally? Are you setting up an agroforestry system or a timber plantation? That's going to determine the mitigation outcome. It's also going to depend on the time frame. So this is just an illustrative figure, but if you were just looking at the very sort of initial part of this is time. It might look like you can capture more carbon from short rotation timber, something like a eucalyptus monoculture plantation that can grow pretty rapidly, compared to natural forest regrowth, which might be a little bit slower. But then once the harvest cycle kicks in, and depending on the fate of the wood, the time average stock can be quite lower for short rotation timber than something like natural forest regrowth. So high uncertainty depends on location, depends on the approach, depends on the time frame, depends on site condition. And so that is what I try to answer, of how do we get robust estimates of reforestation potential, restoration of tree cover. And it really comes down to rates. How much carbon can you get? An area of opportunity. How much area are you putting back into tree cover? And I work along both of those axes, but I think for today, I'm just going to focus on rates. And describe some of our work to improve estimates there, which basically involves me just scraping the carbon literature and pulling it together into tools that people can use. So our first step was just to develop a taxonomy. What are these different approaches for restoring tree cover? There's sort of endpoints that are meant to be natural forest. You can do sort of nothing other than stopping the disturbance. That would be natural forest regrowth. Assisted regeneration might be more of like, you're putting in individual trees to help kickstart the system, serve as a place where birds might land and then poop additional seeds and grow more trees. Whereas active restoration is you've gone out and sort of planted the whole landscape, which is often what people think of when we think about restoring tree cover, but it doesn't have to happen everywhere. Lots of different agroforestry practices, which I'll get into more, and then things that are intended to be sort of plantation. And sometimes this approach is used to transition to a natural forest, eventually with a plantation being the first step along that path. And then we started looking for the relevant literature. The good news is that there actually is a ton of information out there. But the bad news is that it's scattered across hundreds upon thousands of publications. And the decision makers that we're trying to influence don't have access to the literature often, for starters, and definitely don't have the time to sift through all the papers to find the relevant information that they need. And so that's what we do. We spend the time pulling it all together so that it's easy to use. So back in 2017, we started with this large web of science search, putting in a general keyword to try to find things related to biomass and carbon for different approaches to restore tree cover, which brought up 11,000 publications. We fully read 5,000 of those and found about 1,400 that looked like it had the information we needed. We partitioned that by this taxonomy, these different approaches for restoring tree cover. And this took us an immense amount of time to get there. And so we're like, okay, we can't cover all types of restoration of tree cover approaches at once. We're going to have to break off chunks of this at a time. But I'll talk about agroforestry, monoculture plantations, and natural regrowth. today, but I have collaborators working on diversified plantations and active planting currently at the moment as well. This is also a good point to say, I try to use we. All of my work is highly collaborative across multiple organizations around the globe, and I really couldn't do it without many people helping with this work. So I'm here talking to you, but the credit goes to many, many others as well. So we started with natural forest regrowth. And the reason we did that was because it's a good baseline condition by which to evaluate sort of more active forms of restoration, right? It's just nature doing nature's thing. And it's easier to compare across the globe where you can get low versus high carbon accumulations because again, it's just nature doing nature's thing compared to the systems that humans are actively managing, where there's so many different things people can be doing for that forest that will influence the climate outcome. So this is just the recovery of forest cover on cleared lands through spontaneous regrowth due to stopping the prior disturbance or land use. To be included, the studies had to provide an empirical measure of carbon. So that's the approach we take, is really to get those field-derived estimates. And it had to have a stand age that was sort of within our priority window, which is sort of the 5 to 30-year-old forest, because a lot of climate goals are pinned at the sort of mid-century 2050, and that's less than 30 years away now. And a geolocation. And for soil, we need it to have a comparison, right? Like it doesn't just help, and this happens a lot. Someone just gives you a soil carbon estimate for a location. You're like, well, great. Did it go up? Did it go down due to the restoration of tree cover? You have to have that point of comparison. And then there was lots of work to extract the data, lots of work to harmonize the data. And in the end, we had over 13,000 estimates of carbon stocks in recovering forest with a known location and stand age. And I should flag that all of these data are publicly available. You can access them through GitHub if you'd like them. So then we had our data set built and we could start analyzing it. And we tried to figure out what are the principal predictors of variation in carbon accumulation. And we looked at the type of prior land use. So we had everything from lands cleared by fire, other natural disturbances like hurricane blowdowns, logging, mining, shifting cultivation, crop, pasture. And we asked, okay, is that sort of a consistent predictor? And we did it by biome because you see different patterns of land uses at different biomes. And what we found was, no, it's not globally consistent. There's not sort of certain types of land uses that result in lower rates or higher rates. Then we also looked at the intensity of the prior land use. So we had things from like, a recently cleared landscape where the forests were there just before, so there were seed sources and it's not full of invasive grasses yet, up to things that had been in agriculture for like 100 years, right? There's no rootstocks, no seeds in the soil, like that system's going to be harder to recover. But again, we found that it wasn't globally consistent across our data set. However, what was globally consistent was variation by biomes. So here, what we found was that sort of the warmer and wetter biomes had higher growth rates. So boreal was the lowest cold location, and subtropical moist had the highest. So this was great that we found climate was a dominant predictor, because that allowed us to then build this spatial model of how much carbon we expect to accumulate across forest and savanna biomes. So we took all of our above ground field data, which are the blue dots that you see here, and we supplemented it with 3 national inventory data sets from the US, Sweden, and Australia. Those field data sets or inventory data sets were particularly useful because it helped us to sort of bracket the environmental conditions across the globe. And then we combined them with 66 covariate layers that were related to climate, soil, nutrient, chemical, physical properties, radiation, topography, nitrogen deposition. Put it together in a machine learning model, random forest based, and developed this map, which provides spatially explicit estimates at 1 kilometer resolution of how much carbon we expect to get in this sort of young 1 to 30-year-old forest range. And we find over 100-fold variation in potential carbon accumulation rates from 0.06 up to 6. So even though the sort of macro level patterns are what you would expect, right? Like higher growth rates in the tropics, lower growth rates up towards the poles. Even at a fairly fine scale, we can see substantial variation, like 3-fold variation within a country, for example. So our map can be used to identify areas with the greatest carbon returns per hectare of investment. And the difference between these two is here we've sort of predicted across all forest and savanna biomes. We've cross-hatched the savannas because those rates are not going to apply across the board in these sort of mosaic landscapes. And we flagged like, only applicable in maybe riparian corridors or places that are more suitable for more tree cover. But here it's filtered to just a reforestation opportunity map that was in Griscom et al. So these are the places we think that need tree cover. And you can see there's a lot of variation again across the globe. So this was a good start, but we also wanted to provide the raw data so that it could be used and improved through time. And have these uncertainty maps to show where estimates need improvement. This is based off of variation across different random forest runs. You can see most uncertainty towards the north. And here's another version of uncertainty where we looked at sort of how far we were predicting outside of the environmental conditions of our covariates. And there, again, the north as well as sort of south of the Sahara are the places that are most uncertain. So we added our data to the Forest Carbon Database, which is a great carbon database if you haven't encountered it yet. It's run by my collaborator Krista Anderson-Teacher, who's at the Smithsonian, and is a great repository of carbon data in forest. So we combined efforts and put all of our carbon data up there too. It also helps provide, we also provided refined default estimates for strategy development. So those questions that I get from people like, oh, how much carbon can I get in Uruguay? All right, now we can give you a good answer. But these sort of default estimates that were previously the best available and maybe are still the best available, depending on your opinion, are from the IPCC. And they give you just sort of a default value per ecozone. So it would be like this entire purple blob here would be given a single number in the IPCC lookup tables. And these numbers are commonly used. So this was an estimate that 84 of 99 tropical countries were relying on these defaults. But when we looked at variation within one of those zones, so the lowest to the highest is like the lowest to the highest value that you would see in one of these big blobs. And the black are the values that the IPCC gives. The white are the average values that we estimate. But the main thing was that the main point that I think is important is that the IPCC defaults don't capture 8-fold variation within the ecozone on average. So that's really substantial range just within those locations. So we are able to provide much higher resolution of what mitigation might be depending on where you are in the globe. So the next take home is that the most promising opportunities vary by location. So for monoculture plantations, I work for an environmental NGO. Monocultures are not my favorite strategy for restoring tree cover, and they can have negative biodiversity consequences. But it's an important strategy to consider because it's a very common strategy. So the Lewis et al. Found that 2/3 of high-level commitments for tropical forest restoration involve planting, and almost half of those involve the establishment of monocultures. Very common approach for countries. But despite plantation's dominance, we really lack a robust understanding of how much carbon can be captured within monoculture plantations. There's tons of data out there, but a lot of that information is proprietary. It's held by companies and is not out there in the public domain. So we did what we've been doing, which is just to scrape together carbon data from our initial Web of Science review. Jacob Bukowski, who's at Conservation International and on his way to Oregon State, led this work. We found 424 publications that provided empirical measurements of carbon in above ground biomass in monoculture plantations, and gathered, extracted, harmonized as before, and then analyzed potential biological, environmental, and human drivers that may explain variation in above ground carbon accumulation. Oh, and this paper just came out a couple, maybe 3 weeks ago, recent. This is the coverage that we found, the red dots, and maybe doesn't look like super coverage across the globe, but if you look at what FAO reports for the relative density of plantations across the globe, the density upper point sort of matches where there's dominant plantation industries. And what we found, and I'm just showing you the genus results here, is that almost all of the potential drivers that we tried explain some significant variation in carbon accumulation. So some of the stronger ones were stand age, which is not a surprise, genus, prior land use, plant traits, in particular leaf type, phenology, and whether it was a nitrogen fixing tree, as well as whether the trees were fertilized. Help to influence that. But now we have these curves available that people can use to get robust estimates of the mitigation potential of different monoculture plantation species. So what I'm working on these days is agroforestry. Agroforestry is a particularly exciting option, I think, because when deployed well, they have the potential to capture carbon, of course, but they also have the potential to improve livelihoods and the sustainability of agricultural landscapes and enhance biodiversity. So, it's sort of the triple win, which is a big deal for people that work in environmental NGOs like me, but they have to be deployed well to achieve those benefits. And agroforestry is a really common strategy as well. This was a paper that Meredith Martin, who's now at NC State, led when she was at Yale, where there are all these papers where people say, people are planting the wrong trees, but we don't actually know what trees people are planting. Like, that information just doesn't really bubble up. And so Meredith and her team went through all of the publicly available information for all of the tropical tree planting organizations that they could find, and tried to figure out, what were they planting? Were they monitoring it? How many trees were they planting? And they found that since 1961, there have been 1.4 billion trees planted, or at least reported planted by these organizations. But only about 18% of them mention monitoring. So we don't know what happened to those trees, and only 5% of the organizations mentioned survival, which is sad, because those are failed opportunities to learn what's working and what's not working. But what they found was that the top species that people were planting were agroforestry trees. So cocoa, mango, coffee, teak, it can be both, but maybe more plantations. So, okay, agroforestry, win-win-win potential, as well as something that a lot of people are already interested in and doing. But when it comes to carbon accounting systems, agroforestry is particularly poorly described. And I used to say it was due to a scarcity of data, but since I've started looking, I will stick with just the sheer diversity of types of agroforestry systems out there. So there's lots of different system types. For example, you can have silvopasture, where you just have trees and grazing underneath, hedgerows along field margins. Intercropping is like rows of trees with either crops or grazing underneath. Civil arable is sort of a general catch-all term. Fallow is improved fallows, where people help to sort of guide the trajectory of fallows and have like nitrogen fixing species to help enrich the soil. And multi-strata is often what we think of when we think of agroforestry, like coffee below, shade trees above. And what we've done for a paper that is currently in review was to pull the data from this review that Remy Cardinal led. And he developed new default estimates for the IPCC. And these were the data points he assembled for above ground pools, and the shade, the like paler ones are below ground soil carbon accumulation. And what you can see is that the distribution of carbon density in these systems are pretty overlapping. I mean, we've got them arrayed from sort of low to high above ground carbon density. This is the median value. Silvopasture has less than multistrata. But, you know, saying that you're doing a hedgerow doesn't tell you much about how much carbon you might expect in that system. And in particular, silvopasture had over 100-fold variation, which is what you see. Like somebody can have 1 or 2 trees in a field, or they could have a closed canopy with goats grazing underneath. So agroforestry type is a poor predictor. Then, of course, there's all the different management actions that could happen in an agroforestry system. You know, is it being fertilized? Is it being coppiced? Is it being regularly pruned and the residues are falling into the soil? That's going to matter. And the location where you are. And we have a very poor idea of where agroforestry systems currently occur in the world. We helped to pull together an agroforestry map, but it's just woody biomass and agricultural lands that map shows. And we don't know if that's intentional trees, just someone that hasn't yet cut those trees down. We don't know anything about the types of systems that would be represented there. And they're particularly hard because these systems are really dynamic. So this is I think it's a shade-grown cocoa system in Latin America where we knew for certain that there was an agroforestry system. And if you see, it started out without a lot of tree cover, grew through time, but then there was a clearance event and then it began to establish cover. So depending on when you look, you may or may not find an agroforestry system. Oops, gotta scroll. Oh, I think my computer just froze. Yeah. Well, I'll tell you the next thing you'll see. Oh, mine comes up. There you go. So these are 2 examples of existing agroforestry maps. This is the one we helped to put together, led by Millie Chapman when she was at Woodwell. She's currently at Berkeley, where it's basically a map of woody biomass and agricultural lands. And this is another map that just came out that Lesiv led, that maps different forest management practices across the globe, of which agroforestry is one of them. And for the Chapman map, we deliberately excluded anything with greater than 30% tree cover. And so there's a lot of places where we've sort of entirely missed known agroforestry locations. That was what these black and purple dots are meant to represent, because we excluded those high sort of multi-strata, high carbon density, multi-strata type systems. If you sort of squint, the Lesiv map looks better, but you can see there's a lot of purple dots on this map, and the purple dots are where it doesn't like a known agroforestry location from the literature does not overlap with a Lesiv pixel. So we have a hard time knowing where agroforestry is actually occurring. So our solution is to try to improve the carbon accounting first and foremost, and really answer how much climate mitigation potential can you get from agroforestry, and how does that vary by practice, location, management regime, with the goal of producing, again, a publicly available raw database to facilitate global research. So for folks like you all to use if you're interested. Analyze it as we usually do to figure out what are the principal predictors of variation in rates and stocks, and build a predictive model of carbon storage in agroforestry systems. This is an example of a meta-analysis that attempted to explain variation in carbon stocks for agroforestry. And what they found was like system explains some, prior land use explains some, time explains more, but then there was a good half of variation that they couldn't explain with the factors that they were using. And then, of course, once we figure out what are those dominant predictors, create some sort of tool. It won't be a map like we did for natural regrowth, probably. It'll be, multivariate sort of model where people have to probably answer a few questions, but to produce a best estimate based on those predictors. There are a lot of meta-analyses and systematic reviews out there for agroforestry. We found 22 so far that have been published in the last decade. And what we found was when we compared the literature that each of these reviews drew from to generate their conclusions, that they were focusing on pretty disparate sets of the literature. So across those 22 reviews, there were 536 total papers, but 2/3 of those only appeared once. And at most, there's like 3 papers that appeared across 8 different systematic reviews or meta-analyses. So simply just pulling all of that information together is in itself useful, but we found a lot of additional publications to help augment that database. And I'll say part of it is explainable. Some of these papers just focus on soil, some just do intercropping, some just do China. There's reasons that they don't totally overlap in their literature coverage. But for our purposes, we're trying to get as comprehensive a data set as possible to then do a better job of predicting variation. So a lot of our days are spent answering questions like this. I'm not a robot trying to find all of these papers. And we spend a lot of time tracking things down to the original data point. So we want field-derived estimates, and often what we find is that numbers get sort of recycled either in empirical studies or in reviews, and we don't want duplication in our data set. And we want that sort of rich covariate information that you can only get when you go back to the original publication. So this is just sort of an example of what my life is like. But here's a review. It's a nice review. But then we look at what are everything they cite to get their carbon data. Like, okay, they got their carbon data from this paper. And like, okay, you read that paper and it's like, oh no, but wait, they got their carbon data from this paper. And so then you read that paper and you're like, where did they get their carbon data? And so then you find that they got their carbon data from this paper, which was published in 1982 and describes the Sonoran Desert, mesquite in the Sonoran Desert, which is not an agroforestry system. It got used in the context of Africa where mesquite is invasive. And, this is why it's important to go do the sort of forensic carbon digging to really figure out where the good data are. This is where we are at right now. We've gone through over 20,000 publications at this point. This was our original Web of Science search, which we redid recently because that was back in 2017. As we were doing it, we realized we'd missed a bunch from specifically the journal Agroforestry Systems, surprise, surprise. So we went through their entire catalog to find additional papers. We looked at existing databases that are out there, like the Evidence for Resilient Agriculture that attempts to assemble impacts on crop yield of different agricultural practices. Then did a final sort of keyword search based off of the most common keywords in the papers that were ultimately the ones that had the data we needed. But the most promising opportunity to find these papers was actually just to read the papers and see what they're citing. And this has been most helpful for finding non-English papers. So Spanish papers will often cite other Spanish publications, and we're trying to make this as multilingual as possible. So to be included, it had to describe an agroforestry system. I have that in quotes because we're defining it quite broadly. Things like orchards are in, woodlots, riparian buffers, really any trees in agricultural landscapes. They don't have to be fully sort of tree annual crop intermixing or tree and livestock. It has to be a field-derived estimate of carbon in above ground, below ground, or soil pools. And for soil, again, had to have that reference. And then we excluded things that duplicated data. We were not looking at just flux values. We're taking a carbon stock change approach, things that have poor data quality, et cetera. And we're still building it, but right now we have over 900 papers that had the relevant information. um, 17,000 sites from 90 different countries, and over 12,000 carbon estimates. A good majority of it is from soil pools, which I was surprised by because soil data tend to be sparse and messy, but it makes sense given that these are agricultural systems, followed by above ground. And although we haven't focused on roots or understory or litter, we pull those data when we find them. So let's see, those come to my final take homes, which are that there are multiple ways to restore tree cover. And I didn't make this point, but I'll make it now, is that they differ in suitability in a specific context, right? I'm not trying to tell people what they should do. I'm just saying, here are your options, and here's how they vary in carbon. We're trying to figure out how do they vary also in biodiversity impacts and cost and benefits to people, so that local communities can decide what works best for them and in their given context. The other main take home is that we need to learn from each other and build on what's already out there, right? So let's learn from restoration projects that are already happening. What's working, what's not working, why are things failing or succeeding, and pull together all of the information that's out there into useful forms for decision makers. And because this is a climate change talk, which tends to never be very fun, I'd like to end on sort of a positive note, which is to recognize that we all have power to make a difference. And the things that I remind myself are that it's important to remain stubbornly optimistic. Sometimes it's hard to be optimistic, but if we don't keep trying, we're not going to win. So we have to be stubborn about that. For those of us who are able to make more choices than other about what we eat or what we buy, like those choices have consequences. How much do you fly? Who are you electing? And generally just lend your talents to the cause. It's a very exciting time. I feel like we're on like a 10-year roller coaster where it's like, will we or won't we? Will we or won't we? But the pace of innovation is astounding. And so many people are trying to tackle climate change from so many different angles. And that's what gives me hope and keeps me going. So I am grateful for your time for listening to me today and would love to hear any questions or thoughts you might have.
Thank you so much, Susan. That was really informative and very clearly explained. I like your final conclusion that the best strategy is to leave carbon underground, so to avoid emissions. And then, in addition to that, we should deploy all the solutions that we have. And also, I like your at the beginning when you talk about avoided deforestation as another great strategy to slow down climate change. So now we can go to the questions, but first I have a few questions that are from the students from my carbon management class that read your Nature paper. So for example, Shinji, she asked, one of the uncertainties in the study is using historical forest growth to predict future carbon accumulation rates. How might elevated CO2 levels in the atmosphere and increasing temperatures affect these rate predictions? And what are some ways to account for these uncertainties in future research?
Yes, that's a great question. And actually, we're in the process of redoing that natural regrowth map because before we just did sort of the 1 to 30-year-old forest, but then we were talking to folks at the IPCC and they're like, well, great, do you have the older forest as well? And like we had collected the older forest, but had not focused on that. So we're like, let's try to run the clock out longer for these naturally recovering forest. And when you're running the clock out further, it becomes increasingly important to account for future climate conditions, right? Like when we did 1 to 30 years, we're like, okay, historical data are reasonable proxy for what we'll see over the next 30 years, but that assumption doesn't hold when you go out longer. So we hope to do that. You would get CO2 fertilization and changes in climate conditions. And you'll also get increasing rates of disturbance. And the accounting for disturbance is particularly tough. Bill Anderegg just had a great paper that tried to map the potential for the likelihood of climate-driven risks going forward, but how to use that to modify rates accordingly is going to be tough to do. But we will probably just be able to tackle sort of changes in environmental conditions for our modeling purposes, and just have to flag that there needs to be additional work to account for changes due to increasing rates of disturbance.
Yep. Another question on a slightly different topic. It's from Monica. She asks, how would you assess additionality for carbon credits with natural regrowth?
Yes. Oh, good question. So I am often in the position of trying to encourage people to consider natural regrowth, because it can be much cheaper to do if conditions are right, and can be highly effective. We went out when I was a postdoc at the Smithsonian and planted 20,000 trees, and the trees that grew best were the ones that came up on their own, right? Like not the ones we planted. And I think people forget that trees can grow themselves, right? Like we like to go out and do something and plant them. But one of the good arguments or things to keep in mind with natural regrowth is additionality, right? Like if you go out and plant the tree, you can be like, I did something. That tree wasn't going to be in the ground if I hadn't planted it. But with natural regrowth, it is tougher. There are methodologies being developed that will deploy dynamic baselines. So what you do is you say, I'm deciding to do natural regrowth in this location. And then you, with statistical matching, find other places that are similar, like same ownership, same land use history, same general location, and then watch them through time. So the places where you did the carbon project, does that place perform better than sort of the random but similar locations where you didn't have the carbon project? So that's still in development, but I'm excited about having a dynamic baseline for afforestation, reforestation.
Perfect. This is the last question from students. So I know that this is very hard to analyze within a statistical framework, because usually you don't have the ancillary data. But what do you think are the natural processes that most significantly accelerate forest regrowth? For example, seed dispersers.
Yes. So there's been a good bit of research to try to figure out what are the factors that lead to better regeneration. Proximity to forest is a big one, which includes sort of seed dispersal. You know, when you look at the seed dispersal kernels, even for things that are like windblown, they really don't go that far. So being close to existing forest helps a lot. And that's one of the strategies for assisted regeneration, is to like put a fruit-bearing tree sort of out in the middle of the field, and the birds fly out to it and help distribute the seeds. The other factor is how invade it with grasses. That's another really common one that can really prevent regeneration, and how degraded the soil conditions are. Those are the two sort of biggest ones, I think. And you can get really sort of micro level variation where, you know, you look right and it's recovering fine, you look left and it's not. And usually it's something to do with the prior land use condition and how sort of chock full of invasive grasses it is.
All right. That question, by the way, was from Lisa Wang. So now we can open the floor for questions from the audience. So please feel free to unmute and ask the question yourself, or write it on the chat box.
I can jump in, and you got at a piece of this with kind of your response regarding the additionality of natural forest regrowth. What is your sense for like other barriers to implementation of? Because it seems to me, as you were saying, that pitching a tree planting project is really easy for a consumer or for a carbon project. What barriers or like what research do we need to do to encourage implementation of natural regrowth projects over some of the alternatives?
Yeah. So one of the things that you often see with naturally recovering forests is they don't last very long, because they're viewed as messy or lower value, or they're in a landscape where sort of shifting cultivation is the norm. And so you do need some sort of incentive mechanism, I think, to encourage people to sort of value those early forest. And yes, figuring out where it works in what context. And I think just generally keep reminding people that it's an option. Those would be the ones that come first to mind.
Hi, Susan. Thanks for the great talk. Yeah, I'm wondering what major factors lead to the 8-fold variation between bioclimates you mentioned that occur in above ground carbon accumulation.
Yeah, so this is within the IPCC zones where they see 8-fold variation. They're just very large areas, right? Where you've got variation in topography, you've got variation in soil conditions, you've got variation in precipitation, and it's too coarse for capturing the level of variation that we actually see on the landscape. So 1 kilometer is maybe I don't know if I would want to try to predict at finer resolutions than that. And maybe we're even pushing it with 1 kilometer, but just does a better job of capturing that environmental variation across the globe.
Thank you.
Thanks for the question.
Susan, I have another question. And so you showed that the areas with the largest uncertainty are in northern ecosystems and also in the Sahara. But historically, we have this concept that tropical forests are historically the most poorly sampled regions. How come current estimates in tropical forests in South America, Africa are fairly accurate? Is there been a huge sampling effort in recent years? That question is partly motivated by an original question from Alex.
Yeah, from my experience, the most data in Africa, the tropical forest in Brazil, there's incredible data sets that they have. So it's not sort of a tropical versus non-tropical distinction so much as a sort of continental distinction, I think, for data gaps. And that region with the highest uncertainty is at the margin of where you would consider forests to be suitable. There's big policy initiatives called like the Green Belt to try to prevent desertification from spreading downwards. So there are big tree planting endeavors there, but they're not sort of, it's going to be to more restore a savanna type ecosystem. And we were focused more on forest carbon stocks. So our coverage there was not high.
Okay. More questions from the audience? Okay. It's 3 o'clock, so it's good timing. I hope you can go to bed early today, Susan. You did amazing. Everything was super clear, super informative. Thank you so much for
well, thank you for the invitation.
Thank you. Bye.
Bye.